groups and one for nodal market architectures. And then we'll have a conclusion at the end. So first, we'll start to introduce the OSMOS project in itself, so that everybody understands what the project aims at doing and what the WP2 is within this project. So basically, OSMOS project is all about flexibility. We have a definition of the flexibility that we chose in the project, which is the power system's ability to cope with variability and uncertainty in demand generation and grid over different timescales. And using this definition, we try to address the question of matching the new flexibility needs that we see emerging in the industry with the new flexibility sources that we also see burgeoning in the industry. And the whole question of matching the two together is obviously a very interesting question and a very important question to address. And basically the whole project, if we had to summarize, is addressing that question through different work packages. Just some key figures about the project as well. It's a fairly big project. We have 33 partners involved across Europe. We have a 28 million euro budget, and the project spans over a period of 4 years. So as you can see, we have academics, TSOs, and many different types of partners. The work of the project is compartmentalized into 2 different categories. So on the right side of the screen, you can see we have the demonstrators. So we have 4 work packages. WP stands for work package. We have 4 work packages that are dedicated to testing in real life flexibility solutions or software solutions related to flexibility on the field. And on the left side of the screen, you have more methodology and simulation-oriented work packages. So you have work package 1, which tackles the question of what is an optimal mix of flexibility and how to find one. And right below, we have work package 2, so us, who tackle the market designs and regulations topics, which is basically the idea of if you have an optimal mix of flexibility, what are the market rules and regulations that you need to implement for that energy mix to actually be viable and properly utilized. So if we zoom a bit more into this work package 2, the main objectives is to explore topics that I already mentioned and to elaborate a methodology for addressing the questions of market designs. And the main, I would say the core interest of this work package. Oh yeah, I should have said that I'm the work package leader of this work package 2, which is why I'm also doing the introduction. But the core important thing of this work package is this is summarized in this diagram, and it's the quantitative simulations that we intend to do within the work package 2 of this project. So we really want to base some recommendations or analysis on quantitative simulations and quantitative assessments. So that's what we are trying to do here. This diagram illustrates a summary of all the studies that we are currently doing. So each circle represents sort of a reference point. It's a study from which we can draw on some variations. You have 4 main dots here: a nodal market study here, a nodal market study over here, a zonal market study here, and a zonal market study over here. I'll talk about this one in a few seconds. So as you can see, we have sort of a duplicate. This is because we are using 2 different models for these studies. The model represented in blue is a model from RTE called Prometheus and Atlas. Provide some detail about that afterwards. And the model represented in orange is the model CGRID JMM from UDE, University of Duisburg-Essen in Germany, who will present afterwards. And so we are using 2 models. So why use 2 models? Because basically these models are complementary, and they will enable us to zoom in different phenomena and quantify different things that one single model couldn't capture. So the model on the right, the blue model from RT, is intended to be used on small periods of time and it enables us to model actually the sequence of markets as lived by the market participants. So we really model market participants as in an agent-based model, formulating market orders, putting price on those orders, then a market clearing with the activation of those orders, and finally the response from the market results by market participants. That's the part on the right side of the screen. On the left side of the screen, the more orange model does not model these market specificities, which enables it to actually span across much more broader time periods. So you can simulate a whole year in it. And so you can observe different things using the two models. And basically, the study in the middle is just a sort of a bridging study so that we can compare the two models on some common ground. And the presentation is structured according to this diagram, actually, because what we will do is we are going to zoom on the current work and the current status of the work as it is now in the 4 main points. So we are going to start by this point here. Then UDE is going to present their study, the zonal study here. Then we're going to move on to the zonal study on our side, and then end with the nodal study on UDE side. So without further ado, we are going to start with the study from RTE using RTE's model, Prometheus and Atlas. And to do that, we need to first understand what this tool does. And basically, the interest of this model is to represent market participants that are evolving into a market environment. So they have some information and they formulate market orders. So with the whole question of pricing these market orders, putting the proper volume on these market orders, putting the proper links between those orders, because you can formulate complex orders within this tool. And so we want to model that sort of in detail, or let's say realistically, to actually find the more interesting results about the price signals that are built upon such market environment. And by doing so, by going into this detail, we can actually represent the fact that market participants receive information that that gets more precise as we get closer to real time. So this is a very interesting thing that we'll explore in these studies, and it's the impact of uncertainty and how it unfolds with time on the market prices that result from the simulations. So to do that, to do all of these simulations, we take a two-step approach, we could say, and all of this is summarized in this single slide. We first start with what we could call a long-term planning. So we simulate how the market participants would do their long-term planning. And then we go into the short term and we really model the market decisions, unraveling one after another on the day-ahead market, etc. And if we get in a bit into more detail, when we do the long-term planning, we actually use a specific tool that is an open source tool that was developed by RTE, which is called Ontario Simulator. You can see the logo here, and I've put a link below. It's a tool that's massively used at RTE and beyond for power system simulations to address adequacy issues, for example. So you input an energy mix and it optimizes across thousands of Monte Carlo years on an hourly basis, and then you can make proper analysis of different indicators that may be of interest to you. And this tool makes pure and perfect competition assumption, but which helps it to optimize over a very long, over this number of Monte Carlo years that I just mentioned. And so it's of great interest for doing the long-term planning and providing a long-term vision to the market participants. So what we do is we launch this tool 3 times with 3 different scenarios. We take one scenario as an input, and we, using some historical data on forecast error on wind power, solar power, and load, we change the net load according to realistic errors that could happen. And we launched the tool, so 3 times, to have different scenarios. One that is medium, this is basically the initial scenario untouched, and the high scenario and the low scenario are just sort of caps, because the probability that they materialize is still low, very low, but there are sort of boundaries for the long-term vision of what could happen in the short term afterwards. So more concretely for that study, we used one scenario from work package 1. So remember, WP means work package. So we use one of their outputs. It's called current goals achieved. Now, I'm not going to go into detail about what's inside this scenario because it's part of the work from WP1, and we have a complete deliverable that details the findings of work, several deliverables actually that details the findings of the work package 1, and that it's public, it's online on OSMOS's website, and you can read it whenever you want. I think there's also a webinar that was recorded on that topic, so definitely check it out if you're interested more about the scenario. Just a quick mention to understand what this scenario is about. If you look at the European scale, it's very close to the TYNDP scenario in terms of capacity per technology. So now that's for the long-term planning part. So we run 3 times the Ontario simulator and we obtain a long-term vision. So basically what we have in this long-term vision is an assumption of the system cost over an entire year, as well as hydraulic reservoir management. So these are the 2 main things that are important to us, because when we then simulate the short-term decision mechanisms, or process, I should say, market participants will have to make decisions and upon the assumption of these marginal costs, the system marginal costs that they anticipated. And also they will try to use their huge hydraulic reservoirs in accordance to what they have in their long-term vision, because you cannot just give them the hydraulic reservoirs and let them optimize it on a short-term basis, obviously. So on the short-term part, we are going to use an ATLAS model, which is why we call it Prometheus ATLAS. It's basically the core things that we use for the simulations. And ATLAS, so it's the agent-based model that's responsible for simulating this market sequence with one event unfolding after another, with the information flowing and getting more precise with time. All of it is simulated in the ATLAS tool. Now, if we get a bit more concretely, if in figures regarding the results or simulations we had with the scenario for work package 1, well, if we run it through the Ontario simulator, the first thing we observe is because work package 1 is focused on very investment-oriented tasks, they use an investment tool for building up the generation fleet in Europe, and therefore it means that we have a bit less stratification in the thermal units, and therefore we sometimes end up having some flat system costs as a long-term vision. So for example, here you have a week where the system cost in France, marginal cost is around 110 euros per megawatt hour, which is basically the marginal cost of the gas units. And if you zoom in, you can find some small variations. So for example, here you have the 11th and the 12th of March of 2030. Yes, I didn't mention it, but the horizon is 2030 for this scenario, and all the figures that we're going to show you for on RT side. Now, all of these remains flat, but you can still see some variations here. And we, for the next slide, we are and the moment where we're going to go getting a bit more in detail about the results, we're going to focus on those 2 days, so the 11th and the 12th of March. Yeah, and you also note that the figures that you see here will be different from those that UDEs will show, and this is because this is the results from, we could say, a first run using this scenario, and we used a different assumption at the beginning on the CO2 price, mainly because it's, well, in the WP1, the procedure that they followed entails they don't have CO2 price because it's a goal in an objective in their decision function. So it means that you will see different figures between these and the one shown by UDE, but at the end of the project, obviously, and when we will continue this work, we will merge all the figures and use the same values. And in the final result, final recommendations, you will be happy to see that we are consistent across the simulations. But now, since you are seeing behind the scenes results, you keep in mind that these are not the same figure that we will find in UDE's presentation afterwards. Now, we've looked at some marginal cost and the shape it had if we took data from the work package 1. Now we'll get to go a bit more details about water values. I'm running a bit out of time, so I will try to be quick on that. So what you can see on the slide on the right side is basically different time series representing the water values of one single hydraulic reservoir that represents all the hydraulic reservoirs of France. And you have, for each curve represents the water values relative to one storage level. So the storage level is indicated, for instance, here in the caption, it's in megawatt hour. And if you don't have that much water in your hydro reservoir, you can see that your water value goes up during the winter, as well as here to prepare for the next winter. And if you don't have that much water, that many water in your hydraulic reservoir, you can see that the water value just decreases in the summer because we obviously need less generation power at that time in this scenario. So this shows that despite the fact that we don't have that much stratification in the thermal units, we still can reproduce the seasonality that we would expect in computing these water values. And I'm not going to go into the detail about how we computed that, except if there are some questions about it. But the result still is satisfying. As you can see, we have the seasonality that we would expect. And if we look at another countries as well, Italy have the same shape. Obviously, it's a bit different because it depends on the shape of the load, on the system within the country itself, of course, but you can still see the same seasonality and the water values going up at the right time and down at the proper time as well. So that was interesting and reassuring to see. Also, you see that obviously water values are sort of close to the marginal cost average. So 110 for France and Italy is the same value. Now, if we get a bit more into detail about what happens when we run a day-ahead market on after we have this long-term vision, we put our market participants in place and run day-ahead market. Then this is the kind of curves we'll mention. Now, in the simulations, we do not represent too many market participants, so we try to simplify things and we try not to introduce too many artifacts in terms of modeling. So we have, for the zonal simulation, 2 market participants per country, one who is the national generation company, we could say, and one who is the national supplier. And so basically one company that will do all the selling orders and one company that do all of the that submit all of the buy orders. It's a bit more complicated than that behind the scenes, but to simplify, it's basically it. So here what you see is the clear quantities of the market participants who represent the generation company, national generation company in our modeling. And so we here we just see that the results are comforting. We see what we would expect. The market orders resulting from the solar power and wind power are all accepted. We see that the combined cycle and gas turbines are sometimes accepted, sometimes not, and it sort of oscillates sometimes. If we get to a bit more in-depth analysis of these intermediary results. Interestingly, in Spain, for example, on the right, you can see that we find again some things we would have expected, but we see them concretely here with such a massive renewable penetration. As you can see, the solar power just peaks in very high values at around noon, and it gives has sort of two effects. We have the electric vehicles charging that rush into this time period for charging. And we have also some power stations that start being out of the money, and that are the market orders are rejected from the market on this time step. So that was interesting to observe. Another interesting thing to observe as well was here on Belgium on the left side, the sort of oscillations of the market orders related to gas units. So obviously we know that gas units would provide flexibility in the market here with such amount of renewables, but we can see it very concretely in this market clearing, as market orders are sometimes the activation of these market orders is a bit oscillating here, as you can see. Now, if we look at prices here on the right side, we put an example of Spain. And what we did is we put the system marginal cost. So you remember the one from the long-term planning. And we put as well the price resulting from the market simulations. Now, interestingly, on this slide, what we can see is actually many things on just a single graphic. So first, we see that there's a lot more volatility when it comes to modeling the day-ahead market using market participants and real market orders being formulated. Well, it creates complexity and rigidity into the system, and obviously, or usually we observe more volatility. We observe it again here, and you can see it can be pretty dramatic. As you can hear, when we have the solar power being massively sold out at around noon, you can see that the marginal system cost from a very long-term point of view would have just decreased at around 80 euros per megawatt hours. But if we do the actual market simulations, we look at 0 per. So it was interesting to see these results already here in the simulations. And also we can note that the price values are obviously impacted by the thermals, the stratification, sorry, of thermals unit variable costs, as we already mentioned in the beginning. I'm going to be very quick on this slide. We need some time for UD as well to talk about their topics on the day-ahead prices for other countries. So here we do not see that much oscillation around the system's marginal cost for all these countries, but we see it's always above for these three. And we also see, because we don't have that in-depth stratification of all the marginal costs, well, the market participants, when they make orders, they add a bit of stratification, but it's not that in depth. So you can see that we don't have that much different values. We oscillate between a few and sometimes middle values. So this is why it looks like this. But we can also see, interestingly, that France, Germany, Belgium here are always in the same price group on these 2 days, or almost always. You can see some price differences at some point, but most of the time they're in the same price group, and there's this is consistent with the fact that the grid is completely unconstrained on these days, but we are in March in this simulation here, in the around mid-March. So that would be it for RT's zonal study and the intermediate results and behind the scenes that we wanted to share with you. And I'm moving the floor to UD for their part.
Yeah, thank you, Maxime. So I will start with presenting the methodology and some key input data, and then I hand over to Florian for presenting the results. So on the next slide, that's just what is to follow, a brief introduction on our set of tools. In fact, as we will see on the next slides, it's not just the joint market model, but it's a whole ecosystem of modeling tools that we use for this study. And then we will show preliminary results here of our zonal market studies. On the next slide, just a few key facts about the joint market model. It is a bottom-up energy market model, which not only covers the day-ahead electricity market, but also the intraday market the markets for reserve power or balancing energy, and especially also markets for district heating. The model has been expanded over the years to cover almost entire EU 27 and some neighboring countries. And the basic idea, and that contrasts with what Maxime has just said about the Atlas model. It's not agent-based here. It is modeling a partial equilibrium on those interconnected markets. And as we know from economic theory, in the case that we have competitive markets, the outcomes of these markets in equilibrium will correspond to the results of an optimization problem. And so what we are modeling are the dispatch of the different generation units and the demand side flexibilities, the storages. And what is specific for this market model is that it uses a rolling planning approach, as shown in the right part of this slide. Here it's simplified. Here we have the day-ahead market loop, which runs from noon one day until the end of the next day. And then on the graph, we see just one intraday loop. In fact, in the implementation that we use here, we have 8 intraday loops or 7 intraday loops and 1 day ahead loop per day. So we can model the arrival of new informations, of updates in forecasts, for example, for wind. And we can then analyze, and we will show preliminary results on that. We can analyze the impact of forecast errors on market outcomes. And besides the basic market clearing equations, the model also includes a lot of technical details on CHP plants, but also on conventional thermal power plants, and obviously on renewables. Next slide shows, and I don't want to discuss all the details, but it shows the entire modeling system over the years. So we have been developing the joint market model together with partners over the last more than 15 years, and we have now a database that includes both power plant data, time series, and other grid data. We have a specific model component called the vertical load model that helps us to model both load and renewable infeed at a granular level that is also suitable for nodal modeling, as we will see in the next case study. Then we have the market model, which is the JMM, which is supported with a specific tool to model in detail the use of CHP and also power to heat in district heating systems. And we have also a separate tool to model grid and redispatch. And we have also developed tools to analyze reconfiguration of price zones as asked for by CACM, the European guideline on capacity allocation and congestion management. Next slide. And then now we move on to what we have done specifically here in OSMOSE and are still continuing to do. So what we will present in the following are preliminary results based on outcomes from work package 1, which models the investments for future energy systems. And we take results from one scenario, which reflects the current objectives of the European Union in terms of decarbonization, and the scenario year 2030. We model EU 27 plus major neighboring countries, 33 countries in total. And what we will see in the following as with some results are especially comparisons between a reference case where we do not include forecast uncertainties, and then a case where we explicitly model, in fact, that has also been part of our work in OSMOSE, to have model of correlated forecast errors that evolve over time and are correlated also between the different regions covered in the model. And here we focus on forecast errors for wind power generation. And with that, for more details on both the input and on the first results, I hand over to Florian Boehnke, who has been the main investigator on our side so far.
So hello, everybody. I hope you can hear me loud and clear. And I'm going to start at the first bullet point, the data input from WP1. We're going to put this, I'm going to present some figures that gives everybody a deeper understanding of what goes into our model. So afterwards, when we talk about our preliminary results, we can see whether or not our results seem logical so far. All right, so we can go to the next slide. On the left side, I plotted the time series that we received from WP1. On the top of the chart, we see the demand in a rather standard pattern. We have the peaks in the winter terms and the valley during spring and summer. On the bottom end, we see the time series for 3 renewable energy sources that are non-dispatchable in our model, except for curtailing them, obviously. And also here we see rather standard patterns. We have a highly volatile wind time series, an almost static line for run-of-river, and standard pattern for PV in feed over a year. Take note that those are cumulated time series over all European or all 33 countries rather. Yeah. The 3 renewable energy sources sum up to a total infeed of close to 1.8K terawatt hours, which make roughly 55% of the demand. And as a result of the left figure, we can see the right figure where I plotted the residual load. What can we learn from this plot? We see that the residual load on a European scale does not go negative, which we see today on country level for some countries in some hours. It does not happen with this input data. On the other hand, we see that it floats between 15 gigawatts, so close to 0 in terms of the whole European energy system, and 372. All right. On the next slide, we can see which other technologies we have that balance or have to balance the residual load. So load means meets demand. We can see that again, those are numbers cumulated over all countries. We see that the electricity system is dominated by gas turbines, so combined cycle and open cycle gas turbines are 2 of the 3 biggest installed capacities per technology. Also, we have a large share of nuclear power plants, and we see a somewhat expected decline in capacities for hard coal and lignite. And yeah, other than that, you can take away that we have a comprehensive input for all relevant technologies that we can use in our model. So that we receive those inputs from WP1. The last 2 things I want to mention, and Maxime already said it, so I'm going to be quick on this. On this slide, sorry. Is we apply currently as an input parameter a carbon price of 18 euros per ton of CO2, which is considerably low, and we are internally discussing on what value to set this. So we, meaning RTE and us, use the same carbon prices. The fuel prices are mainly derived from the World Energy Outlook, so nothing too special here for these values. All right, so far so good for the input parameters. Now we can hop on to the results. As Maxime and Christoph said, they are preliminary, but whoever finds something suspicious can please let me know, so we can adapt maybe or have a look into it afterwards and get better results in the end of the project. Yeah, on the right-hand side, I plotted the average day-ahead market prices for all countries we are looking at for the 2 scenarios Christoph initially mentioned. So the green bar represents the no uncertainty case, and the blue bar represents the uncertainty case. And I want to focus on 2 learnings that we can clearly see in this chart. First one is the day-ahead price range is between 30 to 40 euros for all countries, or nearly all countries, which is in line with the low fuel and carbon prices. We see that 2 countries stand out of this, namely Spain and Portugal. So the countries on the Iberian Peninsula seem to have a bottleneck towards France. So the very high installed capacities for especially solar power cannot be transported to neighboring countries other than between those 2 countries. The second learning we can see regards the 2 scenarios. So usually we would expect that prices for, if we consider uncertainties, would be higher, but those are average day ahead market prices, and the methodology that is applied for our wind forecast time series, for the forecast errors rather, uses stochastic uncertainty elements, and over a year those balance out. So we have on average over a year basically the same prices. However, this doesn't mean that they are equal in each and every hour between the 2 scenarios, which we can see on the very next slide. Right, here I plotted the day ahead prices on an hourly basis, basically the price differences between the reference scenario and the uncertainty scenario. And we see 2 main points in this charts that I want to talk about. First one is we have very dense deviations in both directions in Q1 and 4. So in the first quarter and the last quarter of this chart, which would be the winter periods, where we additionally have more wind than in the summer period. And also we have a higher relative percentage of wind as PV power peaks during the summer period, making the system overall more reliant for those forecast errors. And during the spring and summer period, so roughly spoken in the middle of the chart, we see a very heterogeneous picture. We have, on the one hand, obviously outliers in price deviations. On the other hand, we see that the 0 line gets hit quite a bit. So we have hours where the forecast error does not play a large role in terms for the price findings on the day ahead market. And then additionally, we have a couple of hours where we do see clear differences between the 2 scenarios, also in the summer period. All right, so far so good. So now we have seen that the 2 scenarios differ on an hourly basis. And on the next slide, I want to give an introduction how the prices on the day ahead market and especially intraday market interact for the uncertainty scenario. So now we are only looking at a scenario with uncertainties. And therefore I chose a week, but it could be any week basically, but I chose the first week in February. The market zone is Germany, and hour 1 on the bottom represents 12 o'clock. So if you can still remember, this is the time where we have our 36-hour day ahead market loop. And so what can we learn from this chart? The green line, obviously, as it is stated on top of the chart, is the day ahead price for consecutive loops during this week. And the red line are the last intraday prices. So what does that mean? It basically means I can buy an intraday hour from at different time horizons, let's say 10 hours in advance or 4 hours in advance. I can buy for the same hour. So this is possible multiple times. And here we only have the prices from the last possible hour where we could buy or balance on the intraday market. So to say the live intraday price. And the first takeaway from this chart is that the short-term intraday market reflects, or the prices of the short-term intraday market reflect the uncertainty in the energy system due to our changes in wind power generation, and are therefore very well necessary. And the other thing regarding the quality of the forecast errors is that we can in part see the temporal correlation. So when we think ourselves what happens at hour 1, we calculate the next 36 hours. At hour 3 or 4 rather, 3 hours later, we get an information update. And those 2 underlying information for the wind forecast are correlated in a temporal way. So the further we go away from our initial unit commitment, the larger possibly the forecast error gets. And that's why, for example, if we follow the two lines from hour 1, they are pretty close together at the beginning and then deviate after a couple of hours even more. All right, so yeah, we see price differences between day ahead and intraday prices. And now the last question I want to answer with the preliminary results is what unit groups are responsible for the load changes that are applied and are reflected in the price changes. And therefore I have a slide, the next one, basically. Yeah, so on the right-hand side, I plotted negative deviations and positive deviations cumulated over all countries, just looking at what technology is used. What is a positive deviation? The positive deviation means that we had an initial plan how much we want to dispatch in our day ahead unit commitment, and then the actual dispatched quantity was larger during the day ahead market. So we had to ramp up power plants, and negative deviations logically being the opposite, that we had to have to reduce generation. And we see in the chart that the JMM uses a lot of hydropower and nuclear if possible, because obviously they are the cheapest technologies of those which are plotted here. But the other big group are the conventional power plants, natural gas, lignite and coal power plants. And we think, or we are currently analyzing if there's a relationship between which flexibility options are used during which quarters or during the year. If there is, let's say, nuclear, maybe flexibility options for the summer period, and lignite and nat gas for the winter periods, which could be. Yeah, but anyways, we are currently researching this. And on the other hand, the blue bars on the bottom of the chart, the negative deviations are plotted. So we had to reduce energy, as I just said. And how does the JMM do this? As we can see, the second bar from the right, electric, meaning DSM unit storages, electric vehicles. And the second bar from the left, the pump hydro storage units are used quite a lot. So basically the energy is stored for later points in time. However, if this is not worth it or possible due to technical restrictions, the dispatch of conventional power plants gets reduced in the way needed according to the forecast errors. And one last argument, when we see the amounts dispatched for natural gas, lignite and coal as a reaction for the forecast errors, we see that they are mainly used for this when we put this into perspective with the total generation per technology on the bottom left on this chart. So those technologies play a key role in terms of ramping in both directions. That's what we can take away from this in 2030. So I hope I'm still in time. That's it for our preliminary results. I see some questions popped up, but we will answer them later, I think.
Thank you, Florian. Now it's the time for Sandrine.
Okay, thank you. So now I will present you the nodal market study that we are launching with the RT Prometheus Atlas model. So basically the goal of this study is to simulate a nodal market design from the day ahead to the real time. And more specifically, we are interested in studying the impact of uncertainties in a nodal market sequence. In other words, we want to know how uncertainties, which are defined at the substation level, will impact the dispatch. So here I will present you the study of the perimeter study and basic findings about the uncertainties. So to do this nodal study, we choose to model a small region of France in a nodal way, that is to say, with all the very high voltage substations. It means 400 kV and 200 kV substations. And we choose to only model two small regions of France in that way, and keep the rest of France and the rest of Europe in a zonal way. We choose to do this because we wanted to limit the time of computation and the amount of data to process. What is really complicated in this kind of study is to have good data, and here we needed to have good forecast data in order to assess the uncertainties at the substation level in a nodal market design. So we decided to pick historical measurements from our operational data to have renewable forecast data at the substation level. In that way, we'll preserve spatial correlations between forecast and also temporal correlation. And in order to have a study at in 2030, we scaled all the data with the volumes of 2030. And we also limited the study on 1 week in order to also limit the amount of data. So we choose 1 week of November in which we have a lot of wind production. So next, so here I will show you some graphs about the data that we have, and here you can see each graph is represent the forecast data for one given day. So the dark line is the realized consumption at the national level, and each dashed line represents the forecasted consumption at a given time. So for example, you have the forecasted consumption in day ahead at 11 a.m., the forecasted consumption in day ahead at 7 p.m., and then updates every 3 hours in intraday. So here you have we have all the data for the national level for load, but we also have this for other geographical scope like regional zonal scope. Maxime, if you can move. So here we have this for the regional scope, which is a very small zone in France. So we have this data for this kind of geographical scope, and we have also this data for substations. Maxime, if you can move to the next slide. Yes. So here we have all the data forecasted at each every 3 hours in intraday and for 2 hours in day ahead for each day of this week for one substation, which is Vichy P3. All this data help us to quantify uncertainties and to have a good model for the nodal market, and then we can make some primary results on this historical data analysis. So here on the left you have a graph where we have plotted the root mean square error depending time before real time for different geographical scopes. So in green you have the root mean square error for a substation, and in blue for a small zone in France, and in red for France. So basically this graph shows us that the closer you are to real time, the smaller is your load forecast error. So this is not surprising, but it's really interesting for us is to see that the geographical scope has a huge impact on the uncertainties. Here you see that the substation errors is very, very important compared to the zonal and to the national load forecast error. And we see that even with the zone is even if you aggregate some substations, you have a huge impact. You can reduce drastically your errors. It means by netting and averaging your errors, even with a small number of substations, like 30, because a zone is almost 30 substations, you can reduce the magnitude of your load forecast errors. So we did this for the load, but we also did this for renewables. And here we have also almost the same findings. That is to say, the closer you are to the real time, the smaller is your forecast error. If you are at the substation level, you have a bigger error than at the national level. But what is also really interesting in the renewables is that you see that the uncertainty only decreases a few hours before real time. Here you see that before 10 hours before real time, your uncertainty do not really decrease very fast. It will decrease very fast only a few hours before real time. And this is quite important when evaluating, assessing the nodal market design, because it questions the fact to make the dispatch at a substation level almost one day before real time.
Yeah, so I take over for the preliminary results regarding nodal studies with the joint market model. And on the next slide, just a brief overview on how we use the JMM for nodal market design studies. We look here not at the 33 countries that we consider in the zonal study, given the computational challenges, but we limit ourselves to Central Western Europe, because in a nodal market model, we have to consider all the grid constraints, all the line capacity limitations, also within a country. And so as put here, nodal markets take much better into account the physics of electricity transport, and they should therefore provide a more efficient price signals. That does not mean that prices in nodal markets are necessarily different between different nodes. They will only differ if there are bottlenecks in the grid. And as probably many of you are aware, we have that kind of nodal market designs implemented in most parts of the US where we have competitive markets. The challenge for us in modeling has been especially to connect data on the grid topology, which is made available by ENSO-E within the TY&NDP data set with data about renewable installations, especially since the grid data are available but without geographical information. So you have to make a match using different methods. Next slide illustrates how we have managed to define data at the nodal market. It illustrates the case of wind energy, and we see on the map in the lower part that depending on the country we have and the location, we have different scale of wind generation capacity. We have a huge concentration of wind capacities in northern Germany and Denmark. We haven't modeled UK here, so therefore we don't see bubbles over there. And the basic principle is that we attribute the wind capacity data that we collect at the level of NUTS3 regions, and then we attribute those capacities to the different grid nodes using so-called Voronoi areas, which map each point on the map to the closest grid point. And yeah, so that's also quite some simulation effort that is behind. And here we see a first result that was a preliminary study which only covered Germany. And we see here what I mentioned before. Large parts of Germany have a rather similar day-ahead price here in January 2030. They are all in red, but you see, as you would expect, January, it's a quite windy month, and then in those regions with the highest wind installations, which are in the north and northwest of Germany, you see considerably lower prices at the different nodes, indicated by the green and the brownish or grayish color. And so depending on the infeed situation and the congestion situation, we will see different price patterns in each hour of the day and the year. And the challenge is to compute this for larger areas. And with that, this is just the first preliminary result, and I hand over to Maxime for providing an overview of what is to come next.
Thank you, Christoph. So now moving on to the conclusions after we explored both the nodal and zonal market design studies that we are conducting with RT, between UD and RT. So let's start with the key messages that we think are important after conducting all of these market designs. So the first key message is that obviously the investigation of different market designs is important and it's necessary for studying prospective energy mix and the viability of such mix. It's always good to remind that it's important to also study market designs when we do some prospective studies. The second key message here would be that forecast uncertainties are very important to be reflected in market design studies as well. As you could see from Florian's charts, but Sandrine's charts as well, the way that uncertainty unravels as you get closer to real time is a very important factor in how market participants respond and how power system operators respond to the flow of information. And from the figures that we saw and the variations that we saw, we already know that it's important to build up a proper market design that takes into account these uncertainties and these patterns of uncertainty if we want to have a proper market designs that correspond to the energy mix that we are studying. And the third key message that we think is important to have in mind as well is, while conducting the study, obviously we face the complexity of modeling different things, just like any study. But it was interesting, particularly for the nodal market designs, because obviously of the level of detail that you need to have if you want to do a market design analysis on a nodal architecture. But we also think that it's challenging to model and simulate in practice, but it sort of parallels the complexity that we could face if we implement such market designs in practice. So there were many challenges that we did or did not foresee when conducting the study. So it was interesting along the way to learn that in the modeling part. So that's where all of what we presented here are intermediary results. The project is far from over. We have also many activities going on and continuing. We already have some improved results by by now that we didn't have time to put in the slides yet, but that will be published soon in upcoming deliverables. We also have a second webinar for the same work package 2 of the OSMOS project that will be organized in the fall with a focus more on modeling. So if you have a strong interest in the modeling that goes behind all of these results or all of these studies, feel free to stay tuned on this webinar. We'll send the information as soon as we have them. It's also interesting to note that here we really focused on the market simulation parts, but the work package 2 has a broader set of activities. And we also organized other webinars with another project, EU SysFlex, another European project that also tackles the issue of flexibility. And here we can, for example, talk about TSO, DSO coordinations and topic like this. And for example, here we organized 3 webinars with this other project. And you can see, for example, in the third one here that we will have, I think it's on the 17th of June. We'll talk, for example, on TSO coordination and these simulations that we are also performing on that topic in these webinars. So if you're interested in these different topics and market design activities, stay tuned within the OSMOS project. We'll see that we have many information still to come and to provide to you. So that's it for our presentation. So I thank you on behalf of all the participants. I thank you all for your attention. I can see we already have 7 questions, or I see the number 7 or 7 questions and answers in the dedicated tools. So I guess I leave the floor to the organizer for giving us the questions to answer.
Thank you, Maxime. Thank you all. Yes, now we can start the question and answer